So about low energy electron-molecule collisions with the Schwinger method.
Okay, I'd like to begin by, again, thanking the organizers for inviting me to give this talk. And when I was making up my talk, I sort of made a conscious decision to make it a little different from the kind of talk I might give at a DAMOP or GEC meeting. I kind of think of this meeting as an opportunity to share with you the sorts of experiences we have had as we've gotten into the studies of electron-molecule collisions, give you a little bit of motivation of about the problems as we saw them, what we've done about them, the progress we have made using the advances we've accomplished, and in a sense, where I think we might want to go. Okay, I think that a meeting like this, that would seem to be something we'd want to come away with. Okay, so for many of you, this is going to be a bit of a review, but I think reviews never hurt people. Okay, I've been snowed in enough seminars to know that is the case. Okay, so I'll be talking about low energy electron-molecule collisions, and particularly with the method that we have developed. Okay, I've done this work in collaboration with my senior postdoc, Carl Winstead. Now, low energy electron-molecule collisions are important in many contexts. That's why one has sort of a conglomerate of people here. Early on, one had the more traditional interest, in which people who were looking at modeling atmospheres, people in astrophysics, people interested in discharges, would be interested in. These generally pertain to diatomics or triatomic molecules. That's where we were when I got into this business some many decades ago. Okay? Now we have, over the last 10 to 30 years, sort of a switch where there's been an evolving interest in electron-molecule collisions as they pertain to understanding low-temperature plasmas and, more recently, radiation damage to biomolecules. Okay? One of the things that needs repeated is data in this area are very limited. Okay? Few groups are doing the measurements. Often people say few groups are doing the measurements because they're difficult. They're difficult, but I think there are other reasons why few groups are doing these measurements, which we could discuss later on. But if you're interested in looking at excitation processes, okay, the techniques that are available for doing these studies today, okay, are difficult to apply to polyatomic molecules. Essentially, what you do to try to get cross-sections for excitation of a molecule is you use this so-called energy loss spectra, which you take an electron beam of fixed energy, direct it on the molecule, measure the energy of the scattered beam as a function of energy loss at a series of angles. And from that data, you try to back out cross-sections for the various states that might have been reflected in that energy loss spectrum. Okay? This is difficult even for diatomic molecules, and what is obvious is if we're going to get more data for polyatomic molecules, which I believe is essential for us to make reasonable progress, with the larger number of vibrational degrees of freedom, this is difficult to impossible. Okay? Here's an example. This is a diatomic molecule. Up there you have typical energy loss spectrum. Okay? These represent the various vibronic peaks that are contributing to the energy loss spectrum as a function of energy and at a certain angle. These peaks belong to about 10 excited electronic states of the nitrogen molecule. Okay? Now what you've got to do is to unravel, the contribution from a large number of vibrational levels lying in a large number of electronic states. Okay? In principle, if you know the vibrational energy levels, you know the Frank-Condon factors and the instrument resolution function, you can do it. The difficulty is these vibrational Frank-Condon factors have actual cross-sections have a large dynamic range. When you're trying to do a fit of something like this to a large number of parameters which are associated with each vibronic level in such a large number of electronic states, it's difficult. I'll show you some results today that we've gotten in collaboration with an experimental group of Modi Kaku, where it's for small polyatomic, like water, you really learn how difficult these things are to do. Okay? Now, measurements are difficult, and I thought I would just simply, when we got into this, you might ask, well, what about calculations? And when you started looking at these things with young and bright-eyed, you say, well, they're feasible in principle. What is this problem of electron collisions? It's just an electronic structure with an unbound electron. Well, as in studying bound state electronic structure, it's difficult in practice. Okay? Why? There are several reasons. One of them is the scaling of this problem. Okay? These problems will see scale rather strongly with some power of the number of electrons in the system. Okay? Minimal, they scale about to the 4th power for the very lowest level treatment, and quickly scale to much higher powers of the number of electrons. Okay? If you're trying to treat excitations and you have to deal with nuclear motion, these all add to the complexity. Okay? Wrong direction. What do we want in a method? Okay, this is the question we asked ourselves some years ago. The answer to that was, we'd like to be able to treat general polyatomic molecules, no begging and borrowing about symmetry. We'd obviously like a good physical model. We're interested in low energy, so we're interested in exchange. We're interested in low energy, so we're interested in polarization. As Bob mentioned, in polarization that may not be important, but when you're colliding electrons off of neutral molecules or molecules in general, it's quite important. And we'd like to be able to get electronic excitation as well as elastic scattering. Now, we plugged along on this problem years ago using the more conventional computers. And one of the things we recognized early on is that it's going to be important to exploit high-performance computing. Essentially, this scaling always basically makes it, you cannot do a lot of the problems you'd like to do today because of the scaling. Okay? When you look at when you pose the question that way, you realize that if that is true, and it is, what you ought to try to do is to use the biggest computer to maximize what you can do today. Okay, we all have finite lifetimes. You can wait for so long. But if the problem is scaling rapidly the size of the system, you have no choice but to say, I am going to use the fastest computer to maximize what I can do. And this is why we hooked on this trend over the last 15 years of moving over to high-performance computers. Okay? In response to that, we developed a method which was an extension of a method introduced way back by Schwinger. We call it the Schwinger multichannel method. It's an extension of Schwinger's variation principle to the many-channel case. The original Schwinger's principle was restricted essentially to elastic collisions, and we wanted to extend it to inelastic collisions. The method we developed, retains the critical property of the original principle introduced by Schwinger, that the asymptotic wave function need not satisfy boundary conditions, the scattering boundary conditions. Okay? In this case up here, in the original Schwinger's method, the reason that came about is because every time the wave function appeared in that expression, it was multiplied by the potential. Potential will die at large distances, so the asymptotic behavior of the function didn't matter. Okay? But we have developed a method that goes beyond just simple elastic scattering, allows us to do inelastic scattering, and we've been able to set it up in such a way that even though the Hamiltonian appears in our variation expression, we are allowed to use square integral trial functions because the matrix elements are independent of the asymptotic form of the trial function. There's no free lunch, and the reason we can use this method, essentially, not requiring the asymptotic form of the wave function, is that the Green's function appears. And let me tell you, anytime you have to run into a Green's function, it's computationally expensive. Okay? So we had made some choices. We just had to do something to address the computational load of using this method to look at polyatomic molecules. And back in the late 80s, we had an opportunity to learn a little bit about parallel computing. And we were lucky in a sense of being able to adapt our method to parallel computers. In the late 80s, they were simple things. They were not very advanced. They were a matter of sometimes 64 microprocessors hooked up together so that one microprocessor could speak to the other. We didn't have a whole lot of computer scientists around trying to hold our hands, trying to tell us how to do everything. So we developed some of our own ideas, and basically what we recognized is the way to go about this problem is we had to generate a huge number of matrix elements, and we had to transform those matrix elements over and over and over again. So what we designed is a strategy that would allow us to essentially run our program doing our various matrix elements separately on each processor. Each processor will handle a different piece of the data set. Each processor would construct a piece of a transformation matrix and will be able to literally do all our transformations by what's called distributed matrix multiplication. You're multiplying matrices that are distributed across processors. In those days, as I mentioned, we were looking at about 64 microprocessors. Now, as you all know, these machines have grown up. They contain thousands of processors. So if you have these methods that are very high parallel efficiency, you can anticipate you could achieve really significant speed. When you design this program, we recognize that you have to limit communication between processes to few and efficient steps. And we were able to set it up to be matrix multiplication. Presently, this code runs on either distributed memory or shared memory parallel computers, okay, as well as clusters. So it basically, we had a tool that could evolve as the architecture of these machines evolved. At this point, I'm just going to start showing you just with ball and stick diagrams some of the applications, just by identifying the molecule, and we'll then select a few to make some further comments. Here are a set of alcohols that we've been able to study. We looked at electron scattering. We did elastic collisions with these, relatively high level treatment of polarization. The reason for our interest in this is because we have a collaboration with a Brazilian group, and they're interested in understanding the ignition step in alcohol engines. As many of you know, when you run an alcohol engine, the temperature of the engine is not very high, so you don't think you're going to have electrons running around. However, the ignition step is a matter of sparks, and to model that, we were interested in understanding some of these collisions. So this is an example of some of the applications that we've done. Then, as Tom Orlando pointed out this morning, some years ago, Leon Sanch kind of stunned us all by pointing out that sub-excitation energies, he showed, could in fact lead to single and double strand breaks in DNA. And we got interested in having a look at that. It was known for the behavior of these strand breaks as a function of electron energy. That whatever process was involved was resonant, was occurring strongly at certain specific energies. And we thought we'd look at the attachment of these electrons to the bases, which look like likely candidates for the electron to land. When you look when it was in the vicinity of DNA, these we're looking at the 4 basic bases in our DNA, and down here we're looking at nucleosides, which are essentially a DNA base with sugar hooked on, and here we're hooked on a phosphate group, looking at electron collisions with such a nucleotide. Here you have the pyrimidines. We did the same thing. So these are systems that we've studied. Some of them we've studied them at a fairly high level to identify where these resonances might occur, because that's where we expect the attachment to occur. And we wanted to look and see what might happen when we extend beyond the bases to include the sugar and the phosphate. And we basically got no surprises when you added the sugar and the phosphates. Most of what happens with the DNA base. I just want to sort of go through and show you the kinds of systems we've been looking at. For a while, when the suggestions were made by Jack Simon and Leon Sage that these electrons are probably attaching to the DNA bases, after that there were also suggestions that the electron might attach to the backbone. The backbone of DNA, as you know, is a chain with alternating sugars and phosphates. So we looked at a series of sugars. Okay? We looked at sugar plus phosphates, look around and see what the resonant-like structure looked like in these systems, see whether there were any resonances that might be candidates for attaching electrons to DNA. And we also extended our studies into looking at phosphoesters, the mono, di, and triphosphoester. Okay? I don't want to go through these in any detail, but that gives you an idea of what we've been up to. Each one of those systems we've been able to study. They're not easy calculations, but they're feasible because of our migration to high-end parallel computing. Okay? Somewhere along the way, people kept asking me, well, you've got this method, and give me an idea of how big a molecule you might be able to do. For some reason, I started thinking about Buckyballs. So this is a calculation, the largest calculation we've done. Has a little bit of history to it. I won't go into it. But we essentially decided to look at the collision of electrons with Buckyballs, and we did so at a level of treatment of totally neglect polarization. We've done this over a range of energies, and I'm just showing the higher energies because these are calculations that are so-called static exchange, okay? Where you don't expect polarization to be very important. Okay? We got these results. You can see some sort of oscillating structure at 15, 20 volts, some sort of diffraction effects here. And we kept asking ourselves, is this real? Is it because we are not converged our calculation? What is this due to? What came along some years ago, some years later, was a group in Australia contacted us. They had seen this paper, which was published in about 2006, and told us that they were studying electron collisions with Buckyballs and might we be interested in looking at some higher energies. This thick black line represents the results that the Australian group sent us, and they're normalized to one angle. But you can see at least we at that point decided, well, this structure here is not spurious. It's not a matter of not having converged our calculation, but we could do a system such as Buckyballs at these energies to get reasonable agreement with experiment. Okay? Now, one of the things that we studied extensively are the positions of resonances. But any of you know in this business that to get a position of a resonance is one thing, but it'd be nice to know something in more detail
about the behavior of, say, the differential cross-section that's associated with that resonance, to see how well you're doing. And here are some examples of molecules that are related to the DNA base and related to the sugar. This is tetrahydrofuran. This is pyrazine. Now, these are very recent results that were came out of Australia. And you can see that we're doing pyrazine, black dots, pyrimidine, as I mentioned to you, that shows pyrazine because it is related to the DNA base. This is benzene. What's important is to realize that we are able to describe polarization in a molecule of this size quite well at 3 electron volts down in this region where clearly the cross-section is changing, showing some very interesting behavior. Okay? That's the main, we had published our paper in I think it's, I forget, maybe 09, and we just got this preprint from them. I'm not going to get into comparisons of these because I'm certain that Jonathan is going to comment on it. But here are some results from Gorfinkel using their R-matrix method. Do quite well down here. They have a little bit of difficulty up here, but more recently she has sent us results which have been able to pick up a little bit more of this behavior. So get these differential cross sections gives you some confidence for a molecule of this size that you've captured the collision physics. This is another example of tetrahydrofuran, which people would argue as sort of a model for the sugars in the DNA bases. And you can see here this very low energy range. These red crosses are the data of Modi-Kaku, and these lines represent all calculated cross sections. So if you're interested in this, these dashed lines represent the cross sections when you do not include a Born correction. This molecule has a sizable dipole. So this gives us a chance as we went along to convince ourselves that we could do these calculations, we could do them accurately, and pick up these effects. Oops. Go back there. Here's a sampling of what we did early on, trying to look at the positions of these resonances in the DNA bases. Okay? These are the 4 bases: thymine, cytosine, guanine, and adenine. Now up here is a bit of sort of laundry. Okay? You can see the sort of the red line, the red results, the green results are the results of calculations with substantially large basis sets, but different basis sets. We would have to do the calculation with a respectable basis set, and we'd have to expand it to see whether we could trust the results. And the red line, the red curve here, is a somewhat smaller basis than the basis we use to get the green curve. You can see there is resonance structure here. Comparing the green and the red, this feature is certainly persisting, telling you that there is a resonance hanging around down here, close to about 0.2, 0.4 eV. We have some structure here. These are 2 little peaks here. They turn into 1 peak there, and there's 1 higher up here. In this calculation, we have examples showing 3 different basis sets: the red, the blue, and the green. You see the same thing. The guanine, these get a little bigger. We only did the calculation with a relatively large basis set. You can see the feature. There are 3 pi star resonances, and these are more or less where they are located. Okay? Now, to compare with experiment, they know very few electron collision experiments in which people actually shoot a beam across and watch the scattered beam as a function of energy and angle for these molecules. But Paul Burrow, many years ago, uses electron transmission spectrum and was able to identify, by looking at the current, the position of the resonances. And you can see that he was predicting 3 resonances, 1 there, 1 there, 1 there. In both of these cases, the thymine and cytosine, we were we're predicting resonances. These two first resonances are a bit higher than where Burroughs sees them, but these two in guanine and adenine, you can see he predicts the resonances to be there, and in here we have adenine, 3 of these. Okay. Now, in general, the agreement between the positions of the first 2 resonances in thymine and purine is relatively good. We always seem to be lying well below the 3rd resonance. Okay? Now, why the agreement is poor? The guanine here is simply that when we did our calculation, we assumed one of the 2 tautomers of guanine. There are 2 tautomers, enol and keto form. For whatever reason, we calculated for the keto form. It turns out that in actual DNA, it's closer to the enol form. So there's some differences here that can be explained. In adenine, we did do the right tautomer, the one that would be in DNA of Leon Sanchez experiments. And you can see again, these are the positions of the 2 lowest resonances. The agreement is not bad. Here you have a substantial difference. We haven't explored the reason for this in adenine, but we did look at pyrazine to try to see if we can understand what's happening here. Why do we do much better on the 2 lowest resonances and seem to do more poorly in 3rd resonance? In looking at our results on pyrazine, one of the things we learned is that the reason for this large difference is due to the fact that in this 3rd resonance, you have a substantial contribution coming in from configurations built on triplet excited state of pyrazine. So it begins to look as though instead of a resonance being described by essentially dipole allowed particle hole excitations of the target, here you have to include triplet excitations of the target in addition to that. So in other words, normally when you think of doing polarization, you think of putting in the dipole allowed transitions in the target. That's what a dipolar field does. Well, you also have to include, we believe in these cases here, triplet excitations. Now, what might the consequences of that be for DNA damage? Well, if you are in fact looking at a resonance that's built, contains a substantial amount of excitation on the triplet state, when that resonance decays, there's obviously an increased probability that the DNA would be left behind in a triplet state, which is not going to be too good. As far as I can tell, that certainly is known to cause damage. And we haven't carried out this calculation in any of the DNA bases, but we're pretty certain that based on the similarity between pyrazine and these DNA bases, that's going to happen. So this physics here is interesting. Okay? Now, uracil. In the process of doing our elastic calculations, we decided, in spite of the lack of data, to have a look at electronic excitations of uracil, one of the larger systems we looked at. We looked at the pi to pi star excitations, the triplet, the singlet. We did these in a 2-channel, 3-channel. In other words, here we just include the ground state and this singlet, this triplet excited state. Here we added singlet excited state for the 3-channel calculation, and here is the calculation for the singlet excited state by itself. Here you have cross sections for exciting the triplet state, and when you get to the singlet excitation threshold, we hooked it on, resulting in a 3-channel calculation. This represents the cross section for the exciting singlet state. Now, here's some recent results that Jonathan in 2009, really, Dora and Jonathan published. And if you compare results that he's gotten for the excitation of the triplet state and with these results, which would be the only results that we have for the triplet, you can see the comparison is quite reasonable. So for a molecule of this size, for electronic excitation, this is not bad. Okay? He plotted the excitation of the triplet state just beyond the threshold where both the triplet and singlet are open. But I think you want to compare this with what's lying below there. Okay? Now, here's the last example I want to discuss. This is a result of our first foray into collaborating with a group that's looking at trying to get electronic excitation cross-sections for water, simple polyatomic molecule. We're looking at excitation of the triplet B1. That's the lowest triplet excitation. It's a strongly dissociative state that will almost certainly contribute to dissociation of water in biological tissue. And I want to draw your attention to the red dots and the green dots. Those are separate results, experimental results, using this energy loss and an analysis of the energy loss spectra of water. So you can see that they are significant differences between the results of these two measurements. This is one set of measurements, this is another. Okay? The red line, red dots are the results of by some Australians, and the green dots are the results of Australians, and the red dots an Australian is also involved, the Hargrave. He's working now with Morty Crew in State University of California, Fullerton. Okay? If you look quickly at these differential cross sections, okay, you'll see that we're comparing the results of a 5-channel and a 3-channel calculation. Our 5-channel calculation contains the ground state, the triplet V1, and an A2 state. We chose that A2 state because it's the next one up in energy. We did a 3-channel calculation. Here I'm showing results of Tom, Signal, and Gilles some years ago using their complex cone method. And you can see the agreement is not bad. These are our results. Okay? These are the results of the 3-channel. These are 5-channel. These are the 3-channel. These are Tom's results. But what's interesting is these results, and the dotted line are the results that we get when we scale our calculated cross-section to have them agree with experiment. Why are we doing that? We're anxious to see whether are we getting at least the right angular dependence. Okay? So at this point, it seems that the answer is probably we are. Whether we can go back and do a more extensive calculation, which we have done, to see whether we can actually be able to reduce the need for scaling, we don't know as yet. But this, to our mind, was encouraging. As I indicated, these measurements are difficult. Here you only have a singlet B1 and a triplet B1 state. When you look at the energy loss spectra, you've got a deconvoluted, you have a singlet B1 and a triplet B1. You've got to do some fitting on that, and sort of deconvolution of the energy loss spectrum, and it's not, it's tricky. So they need some guidance, and we need some guidance on it. In addition to the triplet B1, we also did the singlet B1. Okay, and you can see that the typical behavior of these cross sections is different. These are more forward peak, as you expect with the singlet transition. You can see now, however, that the agreement between the calculated cross sections and the measured is much better than we had in the triplet state. In fact, in this case, there's no need for scaling. Our results, Tom's results, are about the same. Same thing here. Same thing there. So this is, for us, it tells us one thing, is that one's going to have to work hard to get some reliable data for electronic excitation if one is going to make any progress. Okay? So I've told you what we did, the theory we developed, how we implemented it, and some applications. At this point, I stand back and ask myself, what's the status of the output? As far as elastic scattering is concerned, we can use this. Say it's almost under control. I think we can do it. Single channel fixed nuclei calculations work well with some exceptions. Very low energies, okay? You've got to worry about non-adiabatic behavior at very low energies. You've got to worry very hard about the long de Broglie wavelength, how to properly account for that. Above the ionization potential, we do not include any coupling to ionization. That's coupling to the ion channel is significant. Again, one knows how to fix it. You can use pseudostates or use a complex absorbing potential, but something would have to be done. Also, even the single channel fixed nuclear calculations, they work well, but they're not going to do too well when you have narrow resonances where vibrations can be important. So that's the status and outlook for elastic scattering. For inelastic scattering, it's anything but under control. What are you going to have to do? Well, you just look across the hall and see what the guys who do electron atom calculations, what they have done. And essentially, what you learn from that is you're going to have to get going on doing many channel calculations. You're going to have to work hard to get accurate descriptions of the target states, and you need flexible one-electron basis sets. Okay? These are things we know have to be done, and I think going forward, that's, if you want to ask some conclusions of my recommendations of my talk, is these are things that should be addressed. And as far as inelastic calculations are concerned, electronic excitation, we're just going to need more benchmark experimental data. I think this is more or less an example of we're going to have to learn by doing. Okay? With people who study electronic excitation of polyatomic molecules off and on, varying levels of approximation. The agreement is never good if you don't have any data, so you can look at someone else's data and believe he's right or he's wrong. Until we start resolving these difficulties with comparison with serious experimental data, we're not going to get too far. Okay? Inelastic calculations for molecules will not soon approach the accuracy now feasible for atoms. That's for certain. And we're going to have to improve our codes, make them run on bigger machines. You're going to have to learn how to design your calculation. I think this is a key part of it. That's where your cleverness will come in. But over the next 5 to 10 years, one certainly expect to be able to compute useful, semi-quantitative data. Okay? So, I'll give you my acknowledgments. We've had collaborations, useful collaborations with Modi Kaku. He's at Cal State University Fullerton, came out of the Jet Propulsion Laboratories many years ago. We've had very useful collaborations with this experiment, Michael Allen, and Birgit Lohmann, an Australian, and Steve Buckman, Australian. And support by BES and National Science Foundation through an international grant for collaborations with Brazilians. And I'm not going to disclose how much of the resources we use at JPL, but it's not a small number. Okay? So when I designed my talk, I thought, maybe I should add a few more overheads. I have about 6 or 7 minutes. But I said, I don't think so. I said, there are 2 major food ingredients to meal. One is protein and one is carbohydrate. You have the protein, so you don't need more overheads sort of filling in the extra 5 or 10 minutes. So I'll just stop at this point and try to answer your questions. Yes?
I have a question about the electronic structure of these resonances in nuclear bases. Electronic configurations describing these resonances in nuclear bases. You probably have some way to describe leading configuration in terms of molecular orbitals. And
well, let me say something that might help you. The way our problem is formulated, okay, if you ask me, we are trying to describe an n+1 electron system. Okay? The description of that is in terms of n+1 1+1 electron stated determinants, exactly the way you would do it in a CI calculation. So in our approach, since we don't have to enforce boundary conditions, okay, the wave function is built up in terms of n+1 stated determinants, all with square integral basis functions inside of the determinants.
yeah, so in terms of these determinants, if you look at the three low resonances, you see nuclear bases. Can you describe what are leading electronic configurations corresponding to this? And in particular, this triplet resonance. Is it a state with 3 unpaired electrons, like pi, pi star, and some third one?
These are shape resonances in the DNA bases.
Right. But
So,
in terms of readings later determined and describing this resonance.
Yeah, it's just basically a pi star orbital, okay, outside on the principal configuration, which is the Hartree-Fock orbital, and plus a whole slew of determinants describing polarization.
Well, pi star probably is the lowest resonance, right? But you have 3 resonances.
Yeah, we have 3 different pi star resonances for this system.
They're all pi star.
All pi star.
And your triplet resonance, which you didn't include.
Well,
is it-
that was in pyrazine. Okay? I mean, for the triplet excitation in uracil, yeah, that was just a pi to pi star. Lowest pi star in uracil.
But where is the extra electron? You have pi and pi star.
Yeah.
Where is the
Well,
third?
we got when you in collision theory, when you excite the electron, you get an excited state. You have to build a piece of your wave function with another electron that describes the scattering electron, right? So if you look at it, you see inside of there's a piece of the wave function describing what looks like an excited state, but it's multiplied by an orbital that's attempting to describe the collision electron that's coming in. Does that help?
But well, you didn't say where this
Okay, he
collision
seems to be
electron
ready
is.
to help.
So the higher line resonance in pyrazine has a lot of there's a hole in the pi space, 2 electrons in the pi star.
So it's
It's
two
got
electrons on the
significant
pi star
2
on the
particle
same
1
pi
hole,
star.
but when you look at the parentage, the extra electron is actually significantly coupled back to the triplet by the pi star.
So it's still 1 unpaired electron type of configuration. So
It's got significant 2 particle 1 hole character.
This is,
That's exactly.
I should mention, this is the work of Irene Nenner and George Schultz. They were the first to look at this empirically and recognize that, yes, this resonance is built, has a major component built on an excited triplet state of molecular energies. In fairness, it's their work.
Can I ask actually on this point? So your resonances are too low for this third resonance.
Yeah, no, too high.
No, you're
too low. You're too low.
Three of them, yeah,
Were the arrows the experiment or the calculation?
the arrows were the experiment.
You're too
So we were
low.
too
Oh,
high.
no,
we're
no,
too high.
no, you're way too high.
Way too high.
They were using
Oh, right.
the arrows were too low.
Yeah, you were saying too low. Yeah, I was confused too.
Yeah, okay.
You went too high. Yeah.
Polarization will push you.
Yeah, that was what I was going to ask. So I now understand. Okay, right.
Tom?
I want to go back to the water case. I mean, these new experiments with Morty Cocker were very gratifying, especially on the triplet. Though the earlier experiments, I think they were done about 5 or 6 years ago by the Australian group, and when I saw those, those were the first, and I think at the time only differential cross sections. And I think, I mean, it was so upsetting because they were didn't even look like our calculations were done on the right molecules. I mean, forward peaking for a triplet. But I was fortunate enough to meet Hargraves a couple of months ago at a GEC meeting, and he explained it. And this really goes to fit. You have to be careful when you look at these experiments. He showed at the beginning, one of the problems of unraveling this experimental data. It's hard enough in a bound. These are dissociative states, and they overlap very strongly. And so the data fitting of the energy loss spectrum involves basically fitting these broad dissociative states with Gaussians. And if they overlap, if you have a triplet overlapping a singlet, and the triplet is very strongly backward peaked, any contamination of the singlet in the analysis of the data will give you completely erroneous results. So what they did to straighten this out was to rely on photoabsorption data, which has basically the same dissociative spectrum. So when you look at photodissociation data, you will completely eliminate the triplets. So once they nail down what the singlet looks like, then they can go back in. And that's why these 2 experiments look so wild.
What they tried doing is trying to find triplet cross sections would have a larger cross section of higher.
Right.
They tried to make some compromises, get out as far as they could, where they expect the triplet to dominate. They try to get some relative measure in the single distance. But it's tricky. But Hargraves is working with more back group on it. But I really think at this point, the appreciation here is that unless we have some good hard data, there's just no way we're going to make meaningful progress on electronic excitation. I know polyatomics doesn't mean huge polyatomics, but even 3, 4, 5 atoms. It's just difficult. A lot of these states are the social continuum. You don't have those nice strand content factors. So it's a mess.
Yeah, on the nuclear side, so you have very nice shape resonances that you can calculate for the bases, also for the sugars. So when you do the nuclear side, when you connect the sugar to the base, are those shape resonances dominated by the base, or are they sort of
Dominated by the base?
They're dominated.
The reason
by
we
the
added
base.
the sugars on and the phosphate is just trying to see, are we going to see any new resonances coming in?
Okay, so it's generally consistent with Jack Simon's?
Yes, nothing much changes. It's the DNA that's the big. I think what Jack Simon's is that one has to remember what Jack is doing is basically identifying points of attachment.
Yes.
It's going to go to the DNA base. Once it gets down to that base, then you have to have nuclear motion. I mean, it's no longer fine. It's no longer signal. It's just a horrible mess.
So the bases are good antennas for capturing them?
Yes, that's what they capture.
Now, regarding to this question, you not include water in your model, right? Because if you are interested to understand the solution, whether or not it attaches to phosphate or to the base, solvent can change it quite considerably.
Well, water is, to put it into my calculation,
Well, in your calculations, you do not have that,
No.
right? But if you want to make direct comparison with DNA with water,
Yeah.
then you can
Right, yeah.
change this relative order.
I mean, we thought about it. We could certainly add a large number of water molecules. We'd have to go speak to my crystallographer friends and see where we want to position the water molecules for them to be really representative and to the minor loop, things like fold. But we haven't done that as yet. But that's doable. I think for the low energy resonances, the high cell resonance, I don't expect to see a big change. When you get higher up, where you